Hello everyone, welcome to the second half of the PowerPoint, although this one won't be as long. Some of the parts in this half you don't actually need to know. I just want you to understand what they mean. First of all, percent solutions. I won't make you calculate this on the test. I just want you to know what it means. So vocabulary. Percent solution is basically percent by volume or percent mass volume, and this is the way a lot of foods label stuff, and that's why I want you to understand it. If you have solvent and solute both as liquids, it's very common to do percent by volume. So you might go and buy, say, peroxide in the health area of the store, and it'll say 3% PV, which means percent by volume. And that would mean that for every 3 milliliters of peroxide, there are 97 milliliters of water. It's a 3 to 97 or 3% solution. That's percent by volume, is volume to volume. And you also have percent by mass, which you'll see sometimes in like health food stores like to label stuff this way. And that simply means mass of solute per volume of solution times 100% since it's a percent. So if I have 3 grams of something in 100 milliliters of solution, that would be a 3% mass volume, 3 per 100 milliliters, 3 grams per 100 milliliters. So just know the vocabulary there. Now there are several properties that depend upon how much of something you have. And these usually use molality, which is another type of measurement of concentration that I just want you to know the meaning of, but you won't need to be able to calculate. And molality is basically, instead of it being moles per liter, it's moles per kilogram of solvent. And we'll get to that in a bit. But first of all, what are these properties that depend upon how much of something you have? And the main colligative properties are vapor pressure lowering, boiling point elevation, and freezing point depression. Now, you may not know the terminology before, but you have done all of this. For instance, you can make water boil at a higher temperature by adding salt to it. So when you add salt to water when you're boiling it, not only are you flavoring what you're cooking, you're also increasing the boiling point of that water. And when I add salt to water, it also lowers the freezing point so that the ice on our sidewalk will melt because its freezing point is now lower. And we also use that in antifreeze so that the water in our, it's also anti-boil in a way, so that the water in the radiator of your car doesn't boil or freeze as it gets hotter and colder. So we use these properties all the time, and they are called colligative properties, right? Now, I'm not going to make you guys know the math for this chapter because by the time I get back, I'm not going to have time to go over it all over and over again. I just want you to understand it's called a colligative property because it depends upon the number of particles dissolved. Now, the first one, vapor pressure lowering. The pressure exerted by a vapor in a closed system is vapor pressure. I increase the vapor pressure if the particles are easily released from solution. If the particles are not easily released, it has a low vapor pressure. So if you've ever heard the word volatile, volatile means a substance with a high vapor pressure because it's easily released from solution. Right? Now, if I add more solute, the vapor pressure can actually decrease. That's because the solute physically gets in the way of the solution coming out. As you can see here with pure solvent, as I add solute, the vapor pressure goes down. So this is called vapor pressure lowering. So the first colligative property, vapor pressure lowering. The vapor pressure is lowered as you add solute. The next one is boiling point elevation. And all of these, by the way, are physical interactions. So for the same reason, solvent is held in solution by the solute. So here, if I add solute, as I heat the solution up, the solute physically creates a barrier so that less solvent can leave. So the solute physically prevents solvent from evaporating or boiling. So that's lowering how easy it is for it to get out, which raises the boiling point. If it's harder for the liquid to escape, you have to raise the temperature more in order to get it to escape. Boiling point elevation. Likewise, once again, freezing point gets lowered. And this is also due to disruption. Notice how here you have an ice particle forming without solute on the left. When I add solute on the right, it physically creates a barrier against more solvent particles freezing. So you have to make it even colder for that freezing to happen. Freezing point depression, the freezing point gets lower. So the more solute you have, the more you can lower it. For example, here's an antifreeze chart. You can actually have a system that will not freeze until negative 76 degrees Fahrenheit. It's Fahrenheit, not Celsius, but that's still really cold. Now, that would mean that you would need 12 quarts of antifreeze per 18 quart system. So that'd be like a 12 to 6, a 2-to-1 ratio of antifreeze to water. It'd be mostly antifreeze, and your car's going to run very sluggish, but it'll still run. We generally run at the 8 to 18 range, depending upon how many quarts you have, but we generally run where your car is fine up to negative 13 to negative 26 degrees Fahrenheit before you need to worry about that antifreeze freezing. If it's below negative 30 Fahrenheit, you want to be careful driving your car. You need to let it sit and warm up before you drive it, because you might have to melt that antifreeze, and you don't want to just be pumping air through your radiator. You need to wait until that solution has melted before you can drive off in your vehicle. Now what this actually does, this is a curve that shows you when something is a liquid. If you notice inside of that fork, that is when a solution is a liquid. To the left, it's a solid, and to the right, it's a gas. The purple line, if you're not colorblind, is normal. The blue line is when you add salt. Notice how the freezing point gets pushed to the left and the boiling point gets pushed to the right. You've increased how much of the time the solution is a liquid. You've lowered freezing point, you've increased boiling point when you add solute. Now just for some quick review, moles of solute, what if I say 1 mole of sodium chloride? 1 mole of sodium chloride is 2 moles of solute. So what's the difference between a mole of a compound and a mole of a solute? Well, sodium chloride in water becomes sodium ion and chloride ion, and that's 2 things. So the solute will be twice as much as the compound. Now if I did calcium chloride, that's calcium and 2 chloride ions, or 3. So 1 mole of calcium chloride is 3 moles of solute, and I believe there's a homework question asking that. You just have to multiply it by the number of particles. Now if I had something like sodium nitrate, NaNO3, that is not 5 things. That is sodium and nitrate. You break it up into the ions. So sodium nitrate, NaNO3, would be 2 particles, or 2 moles. 1 mole of sodium nitrate is 2 moles of particles. So you're not breaking it down into atoms, although that looks like the case in these 2 examples. You're breaking it up into ions and the number of ions. So we did molarity, and I just went over percent values, but these are not the only ways to measure concentrations. Because colligative properties depend upon solute concentration and not the actual compound, but the ions, we have other calculations. And for that we use molality. All I want you to know for molality is that molality means moles of solute per kilogram of solvent. Moles per kilogram. It's not liter of solution, which is molarity. Molarity is moles of solute per liter of solution. Molality is moles of solute per kilogram of moles of solute per kilogram of solvent. And we use a little m to denote that. And I give you an example there, but all I want you to understand is it's moles of solute. And the reason we use molality is because all of those calculations for colligative properties are based upon moles of solute, like actually moles of solute particles is what matters with molality. Another one that I just want you to know what it means is mole fraction. Mole fraction is moles of solute per total moles. And this is used in some, especially with colloidal things and stuff like that. It's more just one other way to use moles. I think food science uses this sometimes. So moles of solute per total moles. And we use an X for mole fraction as its symbol. Now, how do I use molality? I don't expect you to know this for the test. I just want you to understand that molality is directly related to how much the temperature of boiling or melting changes. So the temperature that something boils at or the temperature that something freezes at will change based upon the molality of the solute in there. So an increase in molality will increase how much temperature of boiling is elevated or how much temperature of freezing is depressed. And both of those are dependent upon the number of particles. So let me real quickly say, let's say I had calcium chloride and sodium chloride. Calcium chloride is 3 particles, sodium chloride is 2 particles. If I had 1 molar of each, which one would you expect to increase the boiling point more? Well, the answer is the calcium chloride because it's more particles. Which one would you expect to lower the freezing point more? And the answer again would be calcium chloride because it's more particles. Number of particles is what matters for colligative properties. Now, we've already done molar mass before, but molar mass is the mass of 1 mole of a substance. I can actually use boiling and freezing point changes to determine that, since the changes are dependent upon molality, and molality is dependent upon kilograms, right? And if I know grams per moles of particle, I can know grams per mole, and I can calculate molar mass. This is, I think, a little bit too much to do for you guys over slides, so I just want you to understand that you can calculate molar mass using colligative properties, right? If I know how much the temperature changes of something, I can use that to calculate the molality of something, and I can use that molality to calculate the actual molar mass of something. Now, this is used in analytical chemistry as one of many ways to identify an unknown, because every salt has a certain molar mass, and if I know the molar mass, so like in this example, I would know that I have about 0.034 moles, and if I had 7.5 grams of the compound, and that was 0.034 moles, I would know I have around 220 grams per mole. I could put that into a table and figure out what my unknown is. Now, we're not going to do that, but I just wanted you to understand that you can use colligative properties to figure out the molar mass of a solute. Now, we do it just by using the numbers on the periodic table. So if it's calcium chloride, that's 1 calcium and 2 chlorides. I add their numbers together, and that gives me its molar mass. But if you don't know what the substance is, this is one way of finding it out.